In today's last video, I want to talk some more about heat capacity. So remember how these are defined. So I can define either the heat capacity at constant volume. So CV is equal to the partial of internal energy with respect to temperature at constant volume, or the constant pressure heat capacity, which is the uh, change in enthalpy with respect to temperature at constant pressure. So both of these terms, we introduced them in MEB, and remember in MEB, we always assumed that things were ideal gases, so I often wrote them like this. So CV of T and CP of T to reflect the fact that they are both functions of temperature. But now that we're in thermo, we can no longer assume that these functions are just functions of temperature, because remember Gibbs phase rule says that we need two intensive properties to be specified. So this is only good for ideal gases. Now remember, in an ideal gas, you assume that the pressure doesn't matter because there's no interactions between the particles anyway. But for a real gas, and for a real fluid just in general, the heat capacity is going to be a function of temperature and pressure. And CP is a function of temperature and pressure as well. Now, at this point, you may be thinking, how is it that constant pressure heat capacity can be a function of pressure itself? So think about what this term means, the partial derivative of H with respect to T at constant P. So if I drew myself a pair of axes and I plotted enthalpy on the y-axis versus temperature on the x-axis, and I just plotted what this enthalpy does as I increase the temperature. So I can take a calorimeter or something, I can increase the temperature, measure that corresponding change in enthalpy, and I could do a curve fit here. And CP is going to be the slope of this curve. So that's literally what it means. dH dt at constant P is the slope of this curve, keeping P constant. The problem is that the results of this experiment would only be valid at the pressure at which the experiment was carried out. So let's say I did this experiment at 1 atmosphere, and say I came back the next day and I did the same experiment at 20 atmospheres. I might get a answer that looked more like this, right? So I would say maybe there's a stronger temperature dependence or a weaker temperature dependence, right? So this may be for 20 atmospheres. I'm not going to put a number on it. I'm just going to say P1, P2. Right, so the idea is that results from one pressure do not translate to another pressure. And that represents a problem for us, because if we look up what CP is in the back of the book, they'll oftentimes give us CP assuming an ideal gas. So they will say CP star of T. So the star represents ideal gas. And because of the work in the experimentation that has to be done in tabulating CP for any pressure, usually it's only done at one pressure that's low enough such that you can assume ideal. So if your problem is all about figuring out using what the heat capacity is of a gas for assuming an ideal gas, there's no problem. You can just use this function as it was given to you. However, if the pressure is very high, say 20 or 30 atmospheres, and you cannot assume an ideal gas, it's inappropriate to use this value of heat capacity because it's not for the pressure at which you need. And the best way to illustrate what I mean is by doing an example. So let's take methane in this example, entering a turbine at 600 K and 10 bar, and say it exits that same turbine at 400 K and 2 bar. And your task is to figure out how much work is produced for each mole of gas. So this is more of like an observation problem. Thinking back to like the entropy example that I gave, you could use an entropy balance to figure out if this is even theoretically possible, but say for sake of argument that it is. And draw yourself a process flow diagram. And once again, let's apply the usual assumptions that this is an adiabatic turbine, constant volume, so no expansion or contraction work, no changes in kinetic and potential energy. And we'll say that the energy balance simplifies to, so we've got molar flow rate, so N1 times the change in enthalpy, so H hat 2 minus H, underbars. H underbar 2 minus H underbar 1 is equal to W, shaft work. All right, I can solve for what I want to know. So the problem asks me how much work is produced for each mole. That is literally Ws divided by N. So in order to solve this problem, all we have to do is figure out what the change in molar enthalpy is for this gas. So again, relate what we know to what we don't know. In this case, we want to know what H2 is. So I need to fill this in on the diagram. H2 is a question mark and H1 is a question mark. Although because we have two intensive variables on each side, we could figure it out. So I'm going to relate dH to, in terms of what I want to know. So it's dH, pressure and temperature are the two known variables. dH dP at constant T times dP plus dH dt, dH dt at constant P times dt. And then we have dH dt at constant P. That is literally the definition of Cp. All right, so we have the heat capacity, dt, and now we need to use some calculus tricks to figure out how to simplify this dH dP at constant T. All right, so for this one, let's try to use the expansion rule. So I'm going to write dH dP at constant T, and I'm going to say that my variables K is entropy and L is pressure. So dH dP, I'm going to expand it into dH ds at constant P times ds dP at constant T plus dH dP at constant S times dP dP at constant T. So go back to the first video of today or from last time to look at how the expansion rule, this is just a form of the expansion rule. Remember, I didn't cover how this is derived. We just cover how to use it. So I'm going to use this to simplify some things. First of all, dP dP is 1. And test yourself by thinking about what else we know in this expression. In this case, we know that dH ds at constant P is equal to T, and that comes from the fundamental property relationship for enthalpy. And we also know that dH dP at constant S is equal to V underbar from that same expression, that fundamental property relationship for enthalpy. All right, so rewriting it in simplified form, dH dP at constant T is equal to T ds dP at constant T plus V. All right, now I can plug that whole thing into my expression. So I can say that dH is all of this stuff, this entire term, times dP. And then plus Cp dt. So it's Cp dt plus brackets V plus T ds dP at constant T, close brackets, times dP. All right, now from here, what I could do is to integrate everything. However, this is where we have to stop because I've got Cp dt here. So I need to look up what Cp is a function of not only T, but also P. So if I look up what Cp is in a textbook, that is going to give me Cp star. So not Cp star because we don't have an ideal gas. Remember, methane is entering at 10 bar. So that assumption of an ideal gas is very, very flimsy at that high pressure. So we're going to need a way to relate Cp of the real gas, which is a function of T and P, to Cp star, which is only a function of T. So this is getting into the departure function area of thermodynamics, and that is a good place to stop for today, and we'll pick up with departure functions next time.